how do we make sure that our projects are actually on time, right? And so we will explore, together with Chet, I'm going to take you through an introductory part on some key ideas, and then Chet will take us through some examples of what other companies are doing to be able to answer this question on what is really going to happen on our projects, okay? I want to start with something I found the other day on the web and really took my attention. I'll let you read it. Okay? So I don't know who KL is. All the credits go to KL, but that's what we see. Okay? As professionals, we are spending a lot of time on this left queue, trying to, explain project delays, right? And the question is, can we move to the other queue, right? What are we doing to avoid them, right? What techniques, what thinking is behind all these, okay? And so I just wanted to start with something hopefully a bit funny, okay? Because the next news I bring to you are not that funny, okay? Sorry. In 2013, our friend from McKinsey, and where is Jim Banaszak? Hey, Jim. Published this report, okay? I'm not gonna take you through all the details, but basically what you're seeing is that 90% of the projects incur cost overruns and delays. The average cost increase is 80%, and the average slippage is actually 20 months behind original schedule, and this looks at mining, oil and gas infrastructure. If you are the lucky 2%, please raise your hand. Okay? But the important message here is what they have done last year. Okay? Almost 10 years after. Okay? And the situation across multiple industries, waste on water, railways, is not really changing much. Okay? They analyze about 500 or so projects, roughly, and we're talking about significant delays, significant overruns. Okay? And so there's something happening. Things are not changing, at least fast enough, right? At least fast enough, okay? And so the question is, with this data, do we know the answer to this question? Can we guess the answer to that question, right? Do we want to be another dot in those statistics, right? So what is also happening, and I don't know if you're familiar with this idea of the ability to influence, is a sort of 1975 old schematic that tells us that the influence basically goes down as we move the project, right? Very well known. What we see because of that is that management intervenes at the end. And I think Gary's, your story are basically an example with obviously much more detail of what this means, okay? One of the things that you will see as we go through is that one of the reasons, not the only one, that this is happening is that as we make decisions throughout the project life cycle, the decisions that we make, right, are not helping us to address variability, and also they increase work in process, which is what we mean by WIP, quite significantly. And we're going to explore and explain what this really means. So keep that thought as we go through, okay? But if this is all happening, there should be some gaps. We're not here to do a forensic analysis of what all the different gaps might be. I think Gary already alluded to many of them. But we want to bring your attention to one particular common denominator that we have found as we have worked across multiple projects around the world, different type of projects. And is this idea, okay, not idea, excuse me, but a fact that in our industry, in engineering and construction, in the project world, we put a lot of emphasis on project administration, right? We do contracts, we check progress, right? We do a lot of that. And we have an over-reliance on reporting and forecasting of project progress, right? We do a lot of that for this, okay? But unfortunately, what we don't necessarily focus enough, that's what we're saying here is an underinvestment, is on how we produce. I know this sounds simple, right? But if we want to improve the performance of projects, we need to focus, we need to touch the work. We need to focus on how we work, how we produce, on top of many other things, of course, okay? So today, we're gonna explore what we mean by this and what are the key ideas behind, increasing our investment of efforts, time, attention to the way we produce. So, production management, this is one of the key ideas of our presentation, is that it provides the means to ensure predictable outcomes, okay? We'll share some examples of people like all of us, right? Professionals, industry, companies in the industry that have been able to achieve this over time. These examples are just some of them, right? Companies that are actually able to compress schedule by a significant amount of time, 40% faster, 47% less cost in oil field development, LNG facilities in oil and gas that have been able to reduce cycle times by 52%, becoming a benchmark, becoming much more predictable, significantly much more predictable, as well as a significant reduction on cost, okay? And these are just 4 examples of things, of projects that are achieving quite significant results, okay? The question is, what is the thinking behind what they do, okay? I'm not gonna talk about what exactly they do, but what is the thinking behind what they do, right? How are they looking at the challenge? The first and most important idea, okay, and we can probably spend one day on this slide alone, is that schedules are not representations of production systems. This is a very, very, very important idea, okay? It might not be a new idea to you, but we need to talk about it, right? Our belief that the schedules represent production systems is flawed, okay? And we're going to expand on that. So from a production perspective, once again, Gary mentioned this, the schedules represent, they're a very important tool, if you will, because they tell us what is the demand that the production system should respond to. Okay? So let me give you a simple example. If I have 10,000 piles, right, that I need to drive, and I have 10 months to do it, that means I need to do 1,000 per month. Let's say 20 days every month, I need to do about 50 every day, right? My production system should be able to generate 50, should be able to produce 50 every day, okay? And so when we say demand is a rate, okay? And we use the schedules as a means to establish these rates, okay? What is the production system? What should the production system respond to? If the production system doesn't have the capacity to produce to the scheduled demand, we will experience schedule delays, okay? There's a whole production system on the right, okay, that has certain capacity, and if that capacity, I repeat, doesn't meet the demand, we will experience schedule delays. If the production system has the capacity to meet or exceed that demand, we might have an opportunity to accelerate, and depending on the resources, we may also have an opportunity to reduce cost, okay? And so what these organizations are focusing on is understanding the right side of this equation, okay? The right side of this equation. More scheduling doesn't necessarily give us better predictability. More detail in our schedules doesn't necessarily give us more predictability, right? And so one of the key thinkings, as I said, is we're going to spend a lot of time on the right. This is an schematic, actually an analysis, a real analysis on a project, that what you see on the left is the demand as projected, if you will, by the schedule, right? But when we started analyzing the production system, we learned that the production system doesn't have the capacity to produce that demand, and it's going to be sort of limited, right? Therefore, we're going to have an issue with our schedules, right? And right there, without doing much more analysis, we know that there's a high chance, actually, we're not going to make it, right? And we will become one of those dolls in the statistics, right? And so one of the first steps that organizations are taking is do the analysis of the production system and see, I repeat, if the production system is able to meet the demand or not, okay? So we're not saying get rid of the schedules or anything like that. We never said that. We are saying let's use them, but to understand that demand, okay? And so the schedules in the production system are really two gears, right? If we want to move faster on the schedule and the production system cannot, it's not going to let us, right? The two gears will not move, right? If the production system can do more, we can move it and maybe we can accelerate the other side and they will actually achieve some significant result, okay? So keep that concept in mind as we go through this. So from a production perspective, the idea of a production system is that things will move through that production system, okay? And as they move through the production system, there is a cycle time, the time it takes to traverse, right? Piles, drawings, right? Packages of work, deliverables in engineering, right? Even if you isolate just the engineering box, there is an engineering production system, right? Do we produce in engineering? Right? Yes, we do, right? We produce deliverables, we produce designs. So when we hear about production, it's not just about physical production, in case we're thinking that way, right? We have knowledge work, we have craft work, right? And we can see the entire system as a production, the entire process as a production system. And so one way, once again, the thinking behind what these organizations are applying is the idea of focusing on 4 verbs, 5 levers, and 3 curves, right? And this is sort of the definition of project production management that I'm going to take you through very briefly. When we say 4 verbs, the idea is that because production is about transforming things, right? I transform engineering into something physical, then move to the site, is that we need to focus on the core production activities, how we design, how we make things, how we transport, how we build and commission things. Okay? So if we don't touch these core, right, production activities, we need to stop and think, what are we doing? Right? If we don't influence the performance of these 4 production activities, we need to think about what exactly are we doing. The idea of the 5 levers is that if we want to influence cost, time, and cash, we have 5 things that we can actually play with from a production management perspective. One is we can do a lot of work on the product design, right? Gary mentioned modularization, right? You're touching the product design, but if we modularize a facility, we're going to have huge implications immediately on the production process design. We're changing the one that follows. That's why you see a plus sign, they're actually interconnected, right? If you make one change in one of them, it influences the other one, right? And the production process design, although the production word is not in there, that's what we mean, is not really a schedule, right? It's the how we do the work, right? It's how we do the work. The third component or lever is the idea of capacity. Okay? Capacity and resources are not synonymous. Capacity is a rate, right? And we have some resources that are contributors to the capacity of a system. Engineers in engineering, equipment, even a space, right? And so capacity is another component that is very important in a production system. And the last 2 that I left purposely at the end are typically blind spots in the way we look at the impact of a production system on project performance, right? Inventory and variability. When we say inventory, we don't mean stocks of materials only. There's another element hidden behind inventory, which is the inventory of work, the work in process, the amount of work that is either being processed or the amount of work that is waiting to be processed, right? So there are two components behind inventory here. And variability, you just did a poll on what is your sense of how things change on a daily basis. We are exposed to very variable systems, very dynamic systems in the project world. We all know that, okay? And so the idea is that we can play with all these five as a means to influence cost, time, and cash. You might be thinking, so how is this different than more conventional project management, right? And so we wanted to bring this comparison to discuss that from a project management perspective, we typically see three levers that are actually at play. And these come from the iron triangle mentality, right? Where we can play with the scope and quality, do the schedule and the resources to achieve the same outcome, right? So from a production management perspective, we have much more options to play with, much more realistic, because we're looking at how we transform work and influence the way the work actually occurs. The idea of three curves is basically a simplification of what we're calling operation science. And let me start with the one in the middle quickly, right? So in any production system, if the utilization of the capacity increases to 100%, right, get closer to 100%, we will quickly see that the cycle times will start going up, right? Will start increasing, right? So, but unfortunately, we tend to try to utilize our capacity always to the maximum, right? That has a very negative effect on performance. If you look at the one on the left, and there are two charts in here, but basically, if we have in a system a lot of work in process, excessive work in process, it gets to a point where the throughput doesn't change, right? And we have a lot of work not finished, but open, right? When I was younger, when I was a superintendent building things, one of the things that I was really good at is at opening work fronts. I was a work front opener like you have no idea, but I was not a good work front closer. I struggled, right? I just didn't know all this stuff back then, unfortunately. And so I did not really understand the impact of work in process. And when I say work front, it's obviously a construction example, but in engineering could be the amount of deliverables that we keep open, right, at any given time in a system, right? The more we put in that system, what this is telling us is that our cycle time, now we're looking at the chart to the right, our cycle time is going to go up very rapidly. So if we're trying to be more predictable, if we're trying to compress our schedules, right, one of the things that we need to keep in mind is our ability to reduce the work in process in any production system, physical or non-physical, okay? And by the way, that's not my opinion. I'm not giving you my opinion. I'm describing the elements of operation science, right? And it's going to happen that way on projects. I'm not going to talk about the other one just to move forward, but this is what we see every time that we ask questions for people like all of us in the industry, right, to draw what is the relationship between cycle time and utilization and working process, and we get these sort of noodle soups, right? We are not in agreement as members of the same team, right? As companies in the industry, right? If you look at this, cycle time, let me see if I have a laser here, yep. If you look at the one below, one coming down, this team, the individuals in the team that will believe this is going to happen, they will increase capacity utilization to move faster. The other half of the team will do exactly, well, the opposite, right? So they understand that if they increase capacity utilization, things will actually take longer, right? And therefore, they will try to maintain some level of capacity utilization. But those are two opposite strategies, and we see these in members of the same teams. Is making sense? Right? And so one of the things that the Project Production Institute is doing, including this symposium, is to start creating much more than just awareness, right? Understanding the impact of these decisions on our ability to perform and perform effectively and get our projects through the process, right?
It's with mapping out the process. And there are tools out there that you can use to do so. And once you map the process, there's specific information you have to collect that will tell you how the production process will behave. So we need to know what is the sequence of operations, who does it, what policies are in place to control production. And once you have that data in there, you can start to generate useful insights for your projects. So here's an example of an engineered production system. Their goal was to create 1,700 engineering deliverables. In this case, they were isometric drawings between May of 2020 and October of 2020. At the time, they were considering reducing the amount of people dedicated to this project and putting on another project. But they were struggling with a lot of rework. And so what you can see here is this production process that was mapped. And these three streams of work are the same sequence of operations, but one with partial rework, one with a more complete rework of the ISOs. And they were having difficulty computing how much of their capacity was eaten away because of the rework. So we created this model to tell them and show them exactly what's going to happen if they keep on track with their current plan. There was a team that was installing a massive steel structure on site. And the question arose, struggling a lot with the capacity of their cranes because they were lifting each individual steel component one by one. And so they weren't going to make it because there were just too many lifts and they were constrained on the number of cranes that could fit in that area. So what we took a look at is we investigated a couple different ways of pre-assembly. One without pre-assembly, you can see they totally blew that. The second one, 30% pre-assembly, and the bottom one, 45% pre-assembly. So almost half the work needed to be pre-assembled before it was installed in order to keep up with their current team. And I'm going to open this box in a bit, but when we're modeling production systems, we have two ways of analyzing how the production system performs. You've got analytical modeling and discrete event simulation. We're going to go over a couple of examples of each in just a moment. But at a high level, the analytical modeling allows us to find optimal policies, sort of design the production system so that if those policies are in place, you get the results that you want in your project. And the discrete event simulation allows us to track how the production system is going to behave over time. And we can see whether or not specific deadlines are met. You can see the accumulation of work in process in various parts of the project so you can plan for the space required, things like that. This first project was a 14-kilometer pool road, and we decided to use analytical modeling because the process was quite simple. Essentially what we're doing is we're driving precast piles, sheet piles, pier and beam, and columns and slabs. And so it's a very simple process here at the top. And what this model allowed us to uncover was in each chunk of this process, what's the bottleneck? Because that's really what's driving the rate at which you can go, how fast you can go. And if each chunk, is there opportunity to change some policies to go faster? And how much work in process should we have built up time? What you can see from this previous picture is they have a ton of work that started, but not all work that's finished. What the team reported after implementing some of the strategies that we gave to them was a 300% improvement cycle. And this was actually twice as fast as the classical V applications they would teach them around. So it's a huge gain to that. The way we did this was we took we created a model for each individual workflow in the process. So you got precast piloting, sheet piloting, hollow cap construction, column construction, pier head construction. And in each of these different workflows, we identified potential opportunities to get the schedule savings on right. So in most of these, it was around bottlenecks, adjusting bottlenecks. And in these bottom three, hollow cap construction, column construction, pier construction, there was significant handover size between each team. And so what that was effectively doing was increasing the huge batch and pushing up their cycle times. Now for each of the bottlenecks, each of these bottlenecks contributed a potential delay to each, to the schedule here. So if they didn't address the bottlenecks, then this is what they would expect for an additional delay in the project. It's about 100 days. So for each workflow, one of the critical elements to understand bottlenecks was to map out the capacity utilization of each resource. The team knew they had to add people, but they weren't sure about which people and which equipment to add to increase capacity. And it's important to know this because if you want to go faster, you need to know where you decrease capacity. And the bottleneck is what drives the speed at which your project can dredge your throughput. So if you're adding resources, you don't want to add people here where utilization is basically these guys are standing around all the time. They start to fall off. But one change in a parameter is going to change this profile completely. So it's important to understand when you bring people on and when you're taking people off, when is the best time to do that? When should you be manning up? When should you be taking off? We can help them identify when is the best time to use and bring on additional capacity.
If you go back to the previous one with you, I just want to highlight something important. So
yeah,
you might have noticed that these production system models have these little boxes, the triangle. And so you might be wondering, what are those triangles, right? So the boxes are actually where the work actually is transformed, right? And the triangles is when the work actually waits, meaning nothing is being done to it, right? And if you start adding the time, because there's a time component in these little triangles, right? You start adding all that time across the production system, right? We can measure by modeling, and we can actually measure it, quantify, right? Not a guess, quantifying what happened with the total cycle time. And what we're learning as we do this and this and this all over the world actually is that the opportunity to compress the cycle time is not so much on the operations themselves. Is avoiding that the work waits for available capacity, right? And is the time is in this triangles, right? And so we need to shift our thinking from productivity to the productivity of the system, which we call it throughput, right? They are not the same, right? Okay. Remember, we're not doing a P50, P90, schedule analysis or anything like that. We're not analyzing the right side of that schematic. We're analyzing the left side. Okay. So there was a question.
And yes, for Brady, it trends, I mean, not all work is spread deeply as it goes through the system. So if you have a value of work that sits behind the time queue, is there a way to relatively show the damage that work sitting here versus work sitting later in the system? Because it's not all, I mean, depending on where you're at project, it's not all created equal in terms of the impact. Does that make sense?
if work sits the end, what? I missed that first part.
Well, not all work is created equally as average in the system. The longer the work sits at a certain point, the time that you ignore, the time and expense where it sits might be less than value of the work sitting behind it. So I'm just trying, how do you maintain that as you look at the overall effectiveness of the system?
Yeah, so typically what we'll do is we'll try to understand, at some point all work is connected, right? So we build that into the model.
Well, not all work is created equally as average in the system. The longer the work sits in a certain point, the time and expense where it sits might be less than value of the work sitting behind it. So I'm just trying, how do you maintain that as you look at the overall effectiveness of the system?
Yeah, so typically what we'll do is we'll try to understand, at some point all the work is connected, right? So we build that into the model, how work is connected and how things get pulled through. And so certain streams of work will have to happen, right? And you're going to sit and wait for the last one. And then they get pulled through from there. And then it ripples on down to the end of the system. And so we're able to capture what are those relationships in between the work and pull through the system.
But it is driven by capacity utilization. So as the work comes in, so that's why we call it the second graph. It's actually a combination of variability of the work to be in, how often does the work come in, and how much variation is there in the work itself. But it is driven by the actual utilization that does the work. So that's why you can't really just actually have a single item go into the system and actually determine what the QLab will be. So, yeah. But
So just one more note. Here's the impact of variability. So what we're plotting here, we ran a simulation, I don't know how many minutes, maybe 100 times. And you can see because of variability, because the policies that are chosen for a particular project, there is a distribution of outcomes. This is the completion of the project. So the time that the final task is finished. And what we want to do is we test different strategies to see how can we tighten up this curve, and then how can we bring it to a point where everything fits within the portion or within before a milestone target. So, and then just to recap. So this project team, with the two modeling applications that we gave to them, they were able to achieve 20% scheduled acceleration, 300%. And if you want to read more about this project, there's a paper that was just published, and it adds a lot more detail, and it's posted in construction using Groundtable website.
Yeah. So by the way, we need to acknowledge that this is a piece of work that we did in partnership with our friends from McKinsey, and on some effort that we collaborated with, and we got an invitation by Kurt to talk about it, and so take a look at that article on the Kurt blog if you were interested in getting more details on the story. So the last piece is, as we are trying to answer this question, what is going to happen on my project? Right? We can do the modeling, but as we are executing work, we know that we're going to have to face variability, right? Variability will hit us. So what are teams doing in order to control that impact, right? And also make sure that work in process levels do not actually get out of control, right? And it's the second strategy, which we call it production control, that is coming at play. But when we talk about production control, we don't mean great controls, by the way, okay? Controls is not the plural of control, okay? I repeat, controls is not the plural of control, right? Controls are more focusing on getting progress, but control is more about direction, right? Control is about setting direction. So I don't need to spend a lot of time on controls, but these are examples of what people are doing. They use a baseline schedule, rules of credit, and we devalue, right? That's typical quality controls. That's not what we're talking about here, right? We're talking about the ability to control the capacity, the inventory, and the variability as we go through, right? And we need to put different means and methods on how we do that, right? And that's what you see in these photos. To be able to influence is an example of engineering. Engineers understanding the process design, and this is a construction team understanding as well their own process design as we go through. So we're going to expand on this. Okay, so this engine doesn't replace the current efforts on the scheduling, right? But it actually augments because it is a production control engine. And this production control engine has four main components. The first one is relentlessly focusing on standardizing production processes. Why do we care about the standardization of production processes? Because we can actually compress cycle times, right? Not only standardizing the product, but also the idea of standardizing process. Second component is combining those standard processes to create an integrated production schedule that might look very colorful, because one of the things that we're keen to understand is how the work is flowing and how it changes flows, right? Because we know that what happens in between interfaces, there's a high likelihood that the work will wait, right? That we will have queues. And if we have a lot of work waiting, the cycle times once again get extended, right? And so, and also is understanding the true complexity of the production schedule. Then we do a lot of work on production planning. We make decisions about how we allocate the limited resources that we have, the teams have, on the work, and then get a set of non-traditional analytics. This is not about discourse and CBI, SPI. This is other type of analytics that will augment, right, their perspective. It's almost like giving the teams a different set of goggles to be able to see new opportunities of how they can actually improve their work, right? This is one output. Is an oil and gas company that executed on the same project some piece of work without production control and another piece of work with production control. You can see just graphically, without reading anything, that the one without production control had less certainty, right? A bell curve that is much wider, right? And the actual output with production control, much more predictable, right? So they were able to increase their predictability to about 60%. Why is not 100? We're dealing with variability, right? Right? And so remember, we're predicting. If we are able to predict only 60% of the work tomorrow, right? Look at what they achieved. First gas milestone on train 2 within 1 day of the forecast that was established 9 months earlier, right? Is because what they implemented is that day in, day out, no stopping, week in, week out, right? To be able to control the variability. This is another example in engineering that produced a good amount of POs. The connection between engineering and procurement, as you know, is very tight, right? And they're saying this took a great deal of coordination and production control was instrumental in making it happen. The project manager, we actually started late, as you can see the blue curve, and they finished about 14 days ahead of the schedule by putting, I repeat, this portion, this element, augmenting, complementing what they were doing with the schedules and registers. Okay, this is Terminal 5 in London 2 years back. Still, a lot of people talk about Terminal 5, but they did something exactly that and able to finish the project with a significant amount of savings and time. It was the first UK civil project delivered on time in the last 40 years back then, right? We apply all these techniques. This is another project in Australia. It's a desalination plant in Australia that the team concentrated quite a lot on the way they were producing during the construction, the work, as you can see in this photo, understanding where the variability was coming from, looking at the sequence, making sure that they don't open unnecessary work fronts, they don't create work in process, and also start measuring, right, how they were improving over time in terms of becoming more reliable and able to achieve those results 15, 18 days ahead of their schedule, right? And so we finish with this. What we're saying is, if we follow conventional thinking, the likelihood that our present relate is extremely high, as you saw in those statistics. We need to do something radically different to look at this. And the idea we bring to you today, to think about it, is focus on the production system. Because if the production system doesn't have the capacity to deliver what we want, we are not going to make it, right? More scheduling is not going to help us. More detailed scheduling is not going to help us, right? Any questions?
To me, yeah, great set. One thing I wanted to ask, a lot of the customer, real. I want to go back to your verbs, right?
Mm-hmm.
We're talking about the criticalness of commissioning and start predictability of that. So my thought is, why are they going to prefer touch activate or something yet? Because that is a preference. It's not well, say in that we should be applying these higher principle. That's part right too. So I'm just wondering your thoughts.
No, I agree with you. We can do that. When we say build, implicitly we are included commissioning, but you're making a good point, right? In commissioning, the production system produces systems and subsystems ready to be operated, right? And typically in industrial facilities or even in other ones, we see the transition between construction to commissioning, the transition between working based on areas to work based on systems, right? And what commissioning needs, sequence of specific systems in a specific sequence, is not necessarily what construction releases to them, right? And so the commissioning teams spend a lot of time defining the optimal sequence of commissioning, but what construction gives them is a different kind of work, and things get completely sideways, right? And so what we are learning in terms of commissioning is we can model, we don't have an example here to show you, but we have model commissioning production systems, and they link to this transition from areas to system-based execution. It's a very interesting thing. And there's a lot of batching happening there, by the way, right? Because for a specific system, you might need multiple subsystems. If you are missing one subsystem, the commissioning of the system waits, right? And the batching creates a lot of waiting. Yes, sir.
And all, you have like moves, but I don't either, but not really lost. But over, my speaking up was, I'm sorry, that microphone.
Use this one.
So the actual question I had was, in a commissioning, you typically have 300 pieces of equipment in a specific data center. Each of those has an OEM that has their own unique supply chain, right? So if any one of those pieces of equipment in the commissioning is late, you cannot really commission the entire system. So I really get the concept of project control and how that's different from project controls. That's awesome. My specific question is, how do you model the entire system? You'd have to go to each OEM's supply chain in order to fully understand the constraints of the bottlenecks in each supply chain. And I'm talking about companies like Schneider, for example, that has very complex global supply chains. So how do we model the system while we're trying to understand, each complexity of each supply chain? At the end of the day, as an owner company at Microsoft, everything needs to come together in order to commission it, right? So just wondering how detailed you go into the project control modeling for that.
I have a surprise for you. Ready? What you see here is one of those production systems of one of those companies that you mentioned, right? This particular owner, right, in the data center space, decided to get a bit deeper on one of the multiple equipment that they supplied, right, and analyze it because they smell something wasn't actually going to be okay as they were planning to increase the capacity that was reached, right? And so we can include a lot of supply flows. You're going to see, by the way, this exact very interesting schematic from Brian Green from Beach Connect later today. So keep an eye on what he's going to bring on exactly your question. But this is an example of a module that is fabricated, not in the United States, it's in Europe, okay, more specifically in Ireland, right? And doing that. So we can simplify things, very detailed one, but we can simplify, connect the entire supply chain and all without getting too complicated, right? And sometimes, honestly, in our experience, we see teams trying to simplify complexity versus modeling the complexity, right? If it is complex, it is complex. So be it, right? Let's analyze it, right? And let's bring what's going to be the impact of that true complexity.
Right. So you do this at a high level for each of the various, the supply chains. So you could do it at a high level. You didn't have to go to details. Okay, great. I think it makes perfect sense. So, I really, really like the application of this on the construction industry. I mean, this is very common to the manufacturing retail industry probably 20, 30 years ago. Value stream mapping, Little's Law, that's very, very common there. S&OP planning, demand supply planning, that's very, very common there. But I really like the application of the capital projects construction industry. So I agree with you. I think there's a lot of value, but we do have a lot of work to do. As you guys have said, we've been on this for 10 years now, right? So we definitely have a lot of work to do on this.
That's what we're meeting today. Yes, sir.
So if you're working with the existing project that has large batches of work, like a construction contractor that has left their work packages at 10,000 hours versus 1,600, you have to go back and rework the requirements of that schedule like this to be able to haul it.
We can model because the size of the package, right, has some implications on the batching of the work, right? You're batching a little work or a lot of work, right? And we can model the impact of what happens if the size of the package is big or small, because you'll see, actually, I remember Shema was actually doing an analysis where they, on two sub-projects on the same project, one of the projects had larger packages than the other one for some reason, right? The package was smaller, and those guys were able to move faster just because of the amount of work that was being released into the field, right? They were able to reduce the working process. So size of packaging does have impact. Yeah. Fernando.
Yeah, and one question, you have the production system, and then we have the producers. And one thing we're working on is the culture, all right? How do we change that culture? And the place that I noticed that it really got interested in this was actually in the T5, St. Pancras. How to where the culture was changed through systems like this. But I wanted to get your perspective, on that. Not only from you saw like the knowledge workers, craft workers, but really lots of Kazakhstan, and the knowledge and the craft, is basically World War II communism versus Gulf Coast. There's certain cultures that are in there that have to be attacked, and we're trying to figure this out how we accelerate it. And of course, there's tools out there. I want to get your thoughts on that.
So, craft workers work in the system, right? Work for the system, right? Knowledge workers, you want to make sure that the system works for them, so to speak, right? And so, if you design the production system, physical production system, even if you're in a different country with different mentalities and culture, right? What we have learned is that can be addressed by focusing on a more effective design of the actual production system to mitigate the cultural or even less productive sort of work environment, right? And now a lot of companies do training and things that also help, right? They train the crews, they invest in training centers and things like that, right? But what we have heard is that if you focus on the production system, the cultural factors can be actually addressed as well, right? Because they work in the system.
No, let me go back. As we found, whether we were in China, we were in Kazakhstan, Russia, Korea, we were in Australia, or the US. When this got down to the people doing the work, it provided clear direction, clear understanding, less rework, less confusion, and zero for the people. The cultural challenge was people between there who said, I don't want to do this stuff. I want to do what I want to do. That became the harder challenge of it to build rituals. Yeah. Well, you get somebody to
I think for now you actually hinted on the word technology, right? And if we actually look back maybe 12 years, remember the days we got cell phones? Do we actually change our mindset when we adopt cell phones? Do we actually have to get an IT department all signed off before we all started walking around cell phones? No. I remember the days when big corporations did not allow, employees to have iPhone, but they control it. Remember? And then after a few years, because the mass growth in the use of iPhone, IT companies had to figure out, IT department had to figure out how to incorporate it into their system. So we think technology has a huge role to play. The problem that we see is right now there's a lot of automation of the existing methodology going on. Even if it's optimized, it's reducing maybe your RSIs rather than actually preventing it and looking at it from a perspective. So I think we have a huge opportunity for a crossroad where we can actually use a different framework to generate and use leverage digitalization to change how we do things. Many people work in the system without even knowing that they are part of the system, right? So we actually have this same type of education and training program for the manufacturing industry, believe it or not. Last week we're not doing the same thing. And one of the things that one of the person that actually says, I learned more about the development production system attending a 5-hour course than I did working 7 years ago. Because they were part of the system, they came to work, they operated based on the rules and governance that was provided by the company without understanding how the system works. So I think what we're saying here is let's design the system appropriately. So that I think another thing I want to add to one of the aspects that Lee talks about is respect for people. So let's give them an opportunity to succeed by creating the right environment, which is through the Christians.
One quick, now that you mentioned that, very quickly, I know we're a bit behind, but we saw the other day an application of robotics in construction, which was the use of robots to track progress. Right? There's nothing wrong about that, as long as you understand that the technology is being used to feed the great administration machine, right? The use of that technology will have zero impact on performance outputs, zero, right? Because the robot just goes through and track progress, right? Great, you're using it, but if the connection is made between the use of that technology and their performance, then we have a problem because it's not going to impact anything. Maybe reduces cost of a couple of guys walking around digging, maybe, right? But how much?
Well, if they use it for practice, to validate completion of that's all we have to say. Okay, you guys now do up because work is out.
That's a different thinking. Correct.